Hey guys, been a minute, but today I'm going to give you a quick presentation on proof by contradiction, and also we'll run through an example on Prim's algorithm. Hope you enjoy the video. Now, I'm sort of going to give a heads up. This can be a little bit hard to understand. There are a lot of logical loops here, so you might need to watch this a couple of times or go back through the LMS content, but I really recommend refreshing on both your proofs. Hopefully Callie's video will out soon about proof by induction. This is my video on proof by contradiction. So what is it? So it's proving something by showing that it being false creates a logical fallacy. So instead of showing a pattern like induction does, you're going to establish your theory is wrong and show that a base case cannot hold true while your theory is wrong. So it's not the opposite of induction, it's more like a different approach, more based on logic. Now I sort of include this step-by-step walkthrough like image, almost as a bit of I'm not a huge fan of it. I think there can definitely be steps to proof by contradiction, but unlike induction, they're a lot less rigid. It's going to make a lot more sense when we go through, but mainly it is about stating that original case is false or making an exception to the rule and stating that exception is true, and then proving that exception cannot hold true while your original law is also true or false, depending on how it's contradicting itself. Basically, you're just trying to show there's a logical fallacy that requires your original statement to be true. I'm going to do this right here on prims. So those who remember, prims is an algorithm that finds the smallest spanning tree. So it finds the guaranteed smallest one, and we're going to prove it by contradiction. So we're going to get a graph, we're going to call it G, and we're going to create a prims, we're going to run it through prims and create a minimum spanning tree called S. Now, we'll say this is our G graph, but really I'm not going to talk about the numbers that much as they're not that relevant. Now, we'll assume that instead of S being the minimum spanning tree, there's actually a different spanning tree called U. U is going to be made up of the first n nodes in S, but not all of them. So it's effectively S with some of the fat trimmed off. We'll call it n-1 nodes, all right? This again can be quite complicated, so I'll run through things a little bit slower here. So we're going to let S, n+1, so the first edge that is in S but is not in U, be node X to Y. And we're also going to have a subset of W, that's all the edges in U. Now, since U is the smallest spanning tree, we're saying that as a factual statement, but it's going to be the source of our contradiction. There must be a path from X to Y without that edge, S, n+1. It's also going to say where the endpoint is not within U. So we're going to say that this path is A to B. Again, A to B also just means X to Y. Now, there's a couple of illustrations here. This one's here from the source. If you search up proof by contradiction in prims, that's where most of this information comes from. It's a really nice short little paper. This one here is a little bit more visual. So we could say this one here is our prims one, and we can just say this middle thing here is X and Y. Actually, it works a bit better if we've got this one as X and Y. And we're going to say that these ones aren't actually the minimal spanning tree. This is our U, and this is our path that we actually need. So this would be like the AB path. Lastly, we are going to consider a tree T, which is just U with this X to Y added and the AB removed. There's the link if anyone needs the prim proof. Let's go through our three main contradictions here. So we're going to cover all three base cases for these two pairs of paths. So if path A to B is greater than X to Y, that means T is going to be smaller than U, obviously because T includes X and Y, and U has AB in it. And since U is a minimum spanning tree, we defined that back here. We declared that U is going to be the actual minimum spanning tree. That means that can't be true. So there is no way that A to B is greater than X to Y. The tricky one is if they're equal. So this is the main reason I don't like saying T is S. There's a slight difference here. But basically, if they're the same, so X and Y and A to B, then T would contain all of U plus that one extra edge as prims didn't initially add A to B. This means that T, since T would contain that extra edge now, cannot be a tree. And since by definition we declared here that T is also going to be a tree, they can't be equal. And lastly, 3. If X to Y is greater than A to B, then when we ran it through prims, it could not have been added as prims would have skipped it. Now this does sound a little bit contradictory, not from the fact that we're proving by contradiction, but more from the fact that it sounds like we're saying prims is correct because prims is correct. And I think that's a bit of the flow, but I think you should look a little bit deeper into it. We're assuming that prims is running smoothly, and we know how prims would have worked. probably should have included some pseudocode on prims, and we know there is no way that prims could have added x to y if it didn't consider a to b. So recommend relooking through prims, but just know that if x and y was greater than a to b, then it wouldn't have been added, it would have been skipped. Now, because you've looked at all three of these base cases, it's impossible for you to exist because every state of a to b, if it was greater than, equal to, or less than, contradicts prims and makes an impossible graph. So there can be no smaller spanning tree that prims didn't find. Now, here's a mini wrap up, and we'll talk about steps. So we asserted that prims didn't find the shortest path. Again, we didn't assert that it was incorrect, it doesn't work. We just asserted that it said there was a shortest path, it wasn't the actual shortest path. We created the instance for all these shortest paths where prims would have got it wrong, and we showed that every instance where prims got it wrong, there had to be a logical error somewhere. I understand this can be frustrating, and I understand it can be difficult because it's less step-based. And again, okay not to get it. I really think the important part here is you sort of start thinking about this for some of your other algorithms. Remember, it's not opposite to introduction. So if you find yourself really not understanding contradiction, maybe start memorizing and learning some of the inductions as well. I think for certain algorithms like prims, it is easier to do contradiction than it is induction. But later on, especially things like Dijkstra's, I think Dijkstra's is much easier with induction. So just make sure you at least have a look at both of them and think about which one you can more naturally understand. I definitely think for some algorithms you're going to find that contradiction will work just fine.
I'm sure that was a heap of information to swallow, and I get it can be quite tricky. Remember to check up on the LMS, maybe run through some other examples on other algorithms, and also compare this to Callie's video on proof by induction coming out shortly.